Hello, IB Bio students. So today we're going to continue 8.2 and we are going to focus on the link reaction and on the Krebs cycle. So as you can see from this summary of stages here, the link reaction links the product of glycolysis, which is two molecules of pyruvate, to the Krebs cycle. Now remember that glycolysis happens in the cytoplasm and this pyruvate has to be shuttled inside the mitochondria via transmembrane integral proteins. So the link reaction is going to take these molecules of pyruvate and a decarboxylation process is going to happen, and acetyl coenzyme A is going to be the product of that, and actually two molecules of acetyl coenzyme A. Acetyl coenzyme A is going to drive the Krebs cycle. Since there are two molecules of acetyl coenzyme A, that means that the Krebs cycle is going to spin twice. So then the end result of all of this is going to be two molecules of carbon dioxide from the link reaction and two electron hydrogen carriers, two NADHs. And from the Krebs cycle, you're going to see two molecules of ATP, not much because this ATP is formed via substrate level phosphorylation, four molecules of carbon dioxide through a decarboxylation process within the Krebs cycle, and then the following electron hydrogen carriers, six NADH molecules that have been reduced, and two FADH2 molecules that have also been reduced. So now let's look at each one of these two reactions in a little bit more detail. So if we go and look at the link reaction here, let's first get some definitions and essential understandings. So the essential understanding here is in aerobic cellular respiration, pyruvate, which is the product of glycolysis, is decarboxylated and oxidized and converted into acetyl compounds and attached to a coenzyme A, hence the name acetyl coenzyme A in the link reaction. So that's exactly what happens in the link reaction. So let's look at it down here. Let's see if I can get everything in the screen. So the first stage of aerobic respiration, because remember that glycolysis was anaerobic, so the first stage of aerobic respiration is the link reaction, which transports pyruvate into the mitochondria. Remember that pyruvate made in the cytoplasm needs to get shuttled in the mitochondria. So aerobic respiration is going to use oxygen to further oxidize the sugar molecule for a greater yield of ATP. So the link reaction is named thus because it links the products of glycolysis, which is pyruvate, with the aerobic processes of the mitochondria. So let's see what's happening here. You see pyruvate here that is made in the cytoplasm because of glycolysis. Now pyruvate is going to be transported from the cytosol into the mitochondrial matrix by the carrier proteins in the mitochondrial membrane. And notice that pyruvate, being a 3-carbon compound, is going to lose a carbon. So pyruvate, by the time it's done getting metabolized, it's going to be converted into a 2-carbon compound, which is the acetyl compound. So the pyruvate loses a carbon atom, and that's what we refer to as decarboxylation. And the 2-carbon compound here of acetyl is going to attach to an enzyme called coenzyme A. And hence you get the product of the link reaction, which is acetyl coenzyme A. Okay? Now in this link reaction process, notice that you release carbon dioxide and you release electron carriers as well. So after all it's done, right, considering that glycolysis in the cytosol has made 2 pyruvate molecules, that means that the link reaction also occurs twice per glucose molecule. So that means that the final end product after you are done linking the 2 pyruvates here, because remember you started with 2 pyruvates here, So after you're done linking the two pyruvates, you are going to end up with 2 molecules of carbon dioxide when the link reaction is done, and 2 taxis or electron hydrogen carriers that have been reduced. So you're going to end up with 2 NADHs. So this is the end product of the link reaction as well as the acetyl coenzyme A. So now we're going to see how acetyl coenzyme A works in the Krebs cycle, which is also another aerobic process. So moving on to the Krebs cycle, and the essential understanding here is that the Krebs cycle, in the Krebs cycle, the oxidation of the acetyl groups is coupled to the reduction of hydrogen carriers, liberating even more carbon dioxide. So the second stage of aerobic respiration is the Krebs cycle. It happens in the matrix of the mitochondria. The Krebs cycle has many names. It's also known as the citric acid cycle or the tricarboxylic acid cycle or the TCA cycle. It's named Krebs cycle after the man who discovered its process or metabolic process, Hans Krebs. So in the Krebs cycle, acetyl coenzyme A, which was made by the link reaction, transfers its acetyl group to a 4-carbon compound oxaloacetate to make a 6-carbon citrate molecule. So let's look at how that happens right here in the Krebs cycle. Let me try to move it as much as possible. So here it is. So here is, actually let me move it up a little bit more. Oh, we're good here. So here's acetyl coenzyme A from the link reaction. So here is acetyl coenzyme A transferring its acetyl group to a 4-carbon compound that is here, known as oxaloacetate. Remember that acetyl coenzyme A is a 2-carbon compound. So then 4 plus 2 gives you your 6-carbon compound, which is citrate. Coenzyme A is released and can return to the link reaction to form another molecule of acetyl coenzyme A, right? So what this is happening here is that disassociation of the acetyl group and the coenzyme A. The acetyl group, which is a 2-carbon compound, transfers its 2 carbons to the 4-carbon compound here of oxaloacetate, and it forms that 6-carbon compound of citrate. So then the Krebs cycle is, of course, a cycle, right? So it goes round and round, and it actually has to go around twice, right? Why? Because you have 2 molecules of acetyl coenzyme A, because you initially had 2 molecules of pyruvate. So keep that in mind, that as the Krebs cycle turns, it needs to turn twice. So the Krebs cycle occurs twice. So what happens after you have this 6-carbon compound of citrate? Well, it gets broken down to reform the original 4-carbon compound, right? So because it's a cycle, right? So it's got to come back as a 4-carbon compound to attach to another 2-carbon acetyl. So this 6-carbon compound here gets broken down through a decarboxylation process, and it gets broken down first into a 5-carbon compound and then back into the 4-carbon compound. So when that happens, I'm going to move up a little bit further here. When that happens, carbon dioxide is released here and carbon dioxide is released here. And then also electron carriers are released. Remember these electron hydrogen shuttles or taxis that are picking up these hydrogen ions and electrons and are storing them in the form of energy to take them to the electron transfer chain. So here you see NAD plus getting reduced, picking up that hydrogen ion here. You see it getting reduced here again. You see FAD getting reduced here, and again NADH getting reduced here. So then that means that per glucose molecule or per 2 molecules of acetyl coenzyme A, you're going to end up, because the Krebs cycle occurs twice, you're going to end up with 4 molecules of carbon dioxide. Here's 1, here's 2, but the cycle goes in twice, so that's a total of 4. 2 molecules of ATP, So here's 1, but the cycle goes twice, so then you end up with 2 molecules of ATP produced directly via substrate level phosphorylation, and 6 molecules of NADH. Here we see 1, 2, 3. Cycle goes twice, so that's 6. And 2 molecules of FADH2. Here we see 1, but the cycle happens twice, so then you end up with 2. So the key takeaway here is that the electron carriers here are now going to drive the electron transfer chain, which, remember that through an oxidative phosphorylation process, you're going to get the most ATP, because we really have not gotten a lot of ATP here thus yet, right? We've only gotten 2 molecules of ATP via substrate level phosphorylation, meaning that you need substrate intermediates here to get broken down in the Krebs cycle process. All right, so that's it for today, and next time we will look at the electron transfer chain.